Dr. Ilangova?
I'm here, sir.
Shall we start?
Yeah, we can start, sir.
Thank you.
Sir,
Please tell me whether the slides are visible and whether
yeah,
my
it is
voice is
visible, sir.
audible. Yeah. What about my voice? Is it okay?
Yeah, it's okay, sir. Now it's audible, sir.
Okay. Thank you.
Sir, just 2 minutes, sir.
Ah,
Actually, we announced the participants like we will start by 11:30. Just 2 minutes to wait and start, sir.
okay, no problem.
Yes, sir. Thank you, sir. Sir, we can start, sir.
Okay. Thank you.
Yes, sir. Thank you, sir.
Last session we have the various sources of power distribution in VLSI circuits. Sources also we have seen how that occurs. And also we have proceeded to the switching activity of logic gates, and then we have tried to calculate the switching activity of the logic gates. And then we have compared, and then we have seen that NAND, NOR, AND and OR gates, they have less switching activity when compared to the XOR, XOR, and then NOT gates. So, for the purpose of low power design, the gates which are having minimum switching activity can be preferred. So that is the point that we have concluded in the last session. And in continuation with that, now let us proceed to the next consecutive slides. So this you can see, we all know what is a glitching activity. So glitching activity is nothing but an unwanted activity. So if an unwanted activity for a single stage may be very, it cannot be a considerable one. But in the case of your system which is having cascaded a number of stages of blocks during that time. So this small glitching activity, okay, when it is getting propagated to the entire all the number of stages, then that itself can be greater than a logic 1. Okay, it can be greater than a logic 1 and for a longer period also. Okay, so this glitching activity also should be avoided. Glitching activity also should be avoided. So unwanted switching should be avoided. Otherwise, that will consume power for the glitching power. Okay, it will consume the power for glitching power. Okay. So next, we'll proceed to the next one. That is here. Actually, both the structures implement the same function. Okay, so here, if you consider a AND gate, then F implements A0, A1, A2, A3, A4, A5, A6, A7. So that is a function that's getting implemented in both the ripple structure as well as the look-ahead structure. So the first one is a chain structure and the second one is a tree structure. Okay, so the second one looks somewhat balanced. The second one looks somewhat balanced. Okay, and in the first case we have cascading of stages. And as far as the power is concerned, which one is better? Okay, so if you try to do the analysis, okay, if you try to do the analysis, here you can see for the same, I mean, for a 4-input AND gate, for a 4-input AND gate, here chain structure and the tree structure are used. Okay, so in both cases, the function F implements x1, x2, x3, x4, x1, x2, x3, x4. So that is the function which is getting implemented in both the structure. So which one is better as far as the power consumption is concerned? We try to analyze that one. Okay, so if you see, using the switching activity calculation, what we have done already, if you consider the first AND gate of the chain structure, okay, so that is at the point D, what will be the switching activity? The switching activity will be, we know that for AND gate, the output lies in logic 1 for one case, and for the remaining 3 cases, it will be 0. For the remaining 3 cases, it will be 0. So the switching activity at the point D for chain structure will be 1 by 4 into 3 by 4. So that is 3 by 16. 3 by 16. If you consider the tree structure, there also at the point D, we will have the same switching activity. At the point D, we will have the same switching activity. That is 3 by 16 again. 3 by 16 again. And again, if you consider the point E in the chain structure, now 3 inputs have to be considered. That is x1, x2, x3. Okay. So out of the 3 inputs, we can make out how many possible combinations? That is 8 possible combinations. And out of the 8 possible combinations, for this 3-input AND function, we will have logic 1 for one case, and for all the remaining 7 cases, it will be 0. So that means for the chain structure at the point E, we can calculate the switching activity pattern as 1 by 8 into 7 by 8. 1 by 8 into 7 by 8. So that is 7 by 64. 7 by 64. At the point E, we can say that the switching activity for the chain structure will be 7 by 64. 7 by 64. Similarly, if you consider for the point F of the chain structure, there again for the 4 inputs, if you consider out of the 16 combinations, for one case it will be the output will be 1. For the remaining 15 cases, the output will be 0. So if you want to calculate the switching activity factor there, it will be 1 by 16 into 15 by 16 plus 15 by 16 into 16 will be 256. So it will be 15 by 256 will be the switching activity at the point F. At the point F. Again, we'll come back to the next structure, that is the tree structure. For the tree structure, already we know that for D, it is simply 3 by 16. And similarly for E also, the switching activity factor will be 3 by 16. And for F, it will be, again, all the 4 inputs need to be considered. It will be 15 by 264. 15 by 264. So that means for the chain structure also and the tree structure also, the point D will have the same switching activity. Okay. And for F also, it will be same. but the only point at which these two differs will be at the point E, because for the chain structure, the switching activity for the point E will be how much? It will be 7 by 64 in the case of chain structure, and in the case of tree structure, it will be 3 by 16. 3 by 16. So which one is larger? Which one is larger? Or which one will have the higher switching activity? Forget about the points D and E. Okay, we'll forget about the points D and E. And only variation in these two structures will have at the point E, switching activity at the point E. So now, if you compare the switching activity, which one will be higher? Which one is having higher switching activity? Seven by 64 is greater, or 3 by 16 is greater? So 3 by 16 will be greater. So 3 by 16 will be greater. So tree structure will have. Any of you wanted to reply? So 3 by 16 is larger than 7 by 64. So in that aspect, we can say that chain structure is having less switching activity when compared to tree structure. But at the same time, you can see the glitching activity, glitching power. Okay, so chain structure is drawn for glitching activity, but tree structure is actually a balanced structure, and because of which the glitching activity will be less when compared to the chain structure. So glitching power will be less in the case of tree structure than the compared to the chain structure. Okay. So like this, we have to carefully analyze before proceeding for the selection of the structure, which one will have less switching activity at the same time. If the application what we are trying to design, if it has more glitching activity or it is prone to glitching activity, then appropriately the structure have to be selected. Okay, so in that way we have to think and then we have to select the structure. Okay, so that is what we can do this particular slide. Okay, and the same thing we have tried in the lab also, and that is for the chains implementation and the tree implementation, and then we have compared the power for each of the structure, and we can find that the chain implementation consumes less power when compared to the tree implementation. Okay. Tree implementation. Okay. So okay, so up to this we can understand that the switching activity influences the power consumption. If the switching activity is more, then the power consumption also will be more. Okay, so that is what we would understand. Okay, next. While proceeding to the optimization, at what level we have to optimize them? Okay, we all know that in VLSI design we have various levels of design abstraction. Starting from the system level, then we have the behavioral synthesis level, okay, and then logic level, and then physical design level. So these are the 4 levels of design abstraction. Okay, so at which level we have to apply the optimization techniques. At each of the level, we can perform the optimization. But what are all the advantages and disadvantages of applying the optimization techniques at each of this level? Okay, so you see this particular slide. Okay, so here you can see. So at the system level, if we perform the optimization, we could achieve greater than 70% of power consumption reduction. And then at the algorithmic level, it is 40 to 70%. Then at the architectural level, it is 25 to 40%. Then at gate level, it is 15 to 22%. And then at transistor level, it is 10 to 15%. So that will be the percentage of power saving that we can achieve at each of this level. And At what speed that we can perform the optimization techniques. Okay, so system level is the superficial level, so at which we can perform the optimization in terms of whether it's seconds. Okay, so again, the algorithmic and architectural level we can perform the optimization in minutes, and at the gate level and transistor level it consumes us more time. Whereas it will take hours together in order to perform the optimization because there is a lower level of abstraction. Okay, but what about the error? Error means just in terms of error, or otherwise in terms of accuracy also you can comment. So at the system level, the error will be more. And when we move on to the top level, to the bottommost level, the error will be very less. Okay, the error will be very less. Say at transistor level, you can see that the error is very less. There is in 5 to 10%. 5 to 10%. Okay, so that is very, very important. So in the other way, you can say that accuracy will be very much higher in the case of your transistor level. See, transistor level of design abstraction, transistor design abstraction. Okay, and then accuracy will be less in the case of your system level of design abstraction. System level of design abstraction. Okay, so but the computational resource requirement, if you see at the transistor level, we have to have more computational resource requirement for performing the optimization as well as the analysis or the estimation. But at the system level, we can have relatively low computational resources. Okay, so in order to perform the optimization or estimation or analysis. Okay, so the accuracy will be, power estimation will be very accurate at the transistor level, but at the system level it will be less accurate. But at the same time, the computational resource requirement will be less at the system level, but at the transistor level it will be more. Okay. So that is what this particular slide conveys to us. Okay. So now we have seen the various levels of design abstraction and the advantages and disadvantages of performing the optimization or estimation at each of these levels. But how can we attempt the optimization at each of these levels? Okay, so that is at the system level. Okay, we have certain techniques. Okay, at the system level we have certain techniques to perform in order to reduce the power that is inactive. Say, for example, if your system is complex in nature, and when for the current computation, if some of the hardware modules are not used, those inactive hardware modules may be automatically turned on to save power. Okay, so if you have several modules in your system, and if some of the modules are not active for a particular computation, okay, for a function, then in those inactive hardware modules may be automatically turned on in order to save the power. So that is the first technique. And modules may be provided with optimum supply voltage also. Okay, we can provide an optimum supply voltage for each of the modules. Okay, and these modules can be interfaced by means of level converters. Okay, say for example, if one particular module is operating at a lower level, the another module is operating at a higher level, then we can have DC to DC or level to level converters in order to provide optimal power supply for each of the modules. So there is a second point that can be that can be attempted at the system level. Then some of the energy that is delivered from the power supply may be recycled back to the power supply itself. So we all know that there is adiabatic logic. So in adiabatic logic, so the unused power will be recycled back to the supply itself. Okay. So by doing so, we can again conserve energy. Okay. So that is the power consumption can be reduced. So some of the energy that is not delivered, or that is delivered from the power supply, but that is not used, okay, can be recycled back to the power supply itself. Okay. So that is also possible at the system level. And if you have several tasks, and these tasks can be partitioned, okay, and it can be assigned to each of the hardware modules, okay, so that we can reduce the system level power consumption. Okay, so there is partitioning of the task into subtasks, and then assigning it to various hardware modules can also reduce the power. So it can also reduce power. So these are all some of the system level power reduction techniques. Okay, system design level power reduction techniques. Okay, and next to the system level, we have the architectural plus behavioral level. architectural or behavioral level. So there we can apply the concurrency increasing transformations. Okay, so what type of concurrency? Concurrency in the sense we know that we are parallelizing things. Okay, so concurrency increasing transformations means that is we can go for loop controlling concept. Okay, so in loop controlling, what we try to do is we try to apply parallelism to the computation. Okay, for a particular computation, we are applying parallelism. So that is called loop control. Okay, so that the third, because of this parallelizing, there is a parallelism is involved in the computation. Okay, so even though the area is getting increased, okay, so the power reduction can be achieved. So the important technique, that low controlling technique is the important technique for the flow graph transformation. Okay, so what's flow graph transformation? That is, two output values are produced using two input values. Okay, in a single cycle, single clock cycle for two input values, two output values will be produced. That is called flow graph transformation. So this loop controlling technique is a basis for it is used for flow graph transformations. Okay, flow graph transformation. So other than that, we can also introduce pipeline. Okay, so we pipelining, what we try to do when we have a set of data processing elements which are connected in series. Okay, we are connecting the data processing elements in series, where the output of one element is the input of the next one. Okay, so that will be the case when we try to have the data processing elements in series. Then the elements of a pipeline are often executed in parallel. Okay, so the elements of the pipeline will be executed in parallel or in time-sliced fashion. Okay, so in that case, some amount of buffer storage is often used. Okay? So that is, we'll try to introduce registers in between. Okay? Introduce the registers in between. Yes. Okay, so in between the data processing elements, we can introduce the registers. Okay, so by introducing that registers, okay, then we can reduce the power consumption. And also these placement of registers, that is the location of registers, can also be distributed, or it can be changed and then it can be analyzed. And that concept is called as retiming. Okay, so using retiming also we can try to reduce power. And then control flow optimization. Okay, we have control flow optimization also. So the high-level synthesis tasks such as scheduling, module selection, and resource sharing. So like that, we have several high-level synthesis processes. Okay, so there, that is there we can apply the control flow optimization.
Sir, excuse me, sir.
Yes, Ilangu.
Sir, the slide is not changing, sir.
I could change it. So
You are in level of optimization, right? It means.
No. I'm just giving an introduction on.
Yeah. Oh, sorry, sir.
Various techniques applied in the levels of various levels
Sorry,
of
sir,
optimization. I have not moved the slide. Thank you for the information. Okay, so that is we can go for power conscious structuring. Okay, we can go for power conscious structuring. Okay, so when we proceed with the control flow optimization and also loop optimization, we can do, and then critical path reduction. Okay, so and then so these are all, and we can go for algorithmic specific instruction sets. Okay, instead of going for a generic instruction set, we can go for an algorithmic specific instruction set. Okay, and then providing on-chip cache. So these are all the various techniques. Okay, there are various techniques which are applied at the architectural of the behavioral level of power reduction. Okay, so and the next one is the logic synthesis or register transfer level. Okay, the logic synthesis or register transfer level, and there we can provide proper binary assignments. Okay, for your FSMs, that is finite state machines, in order to minimize the switching activity. And also, as I told already, the retiming can be applied here also at the logic synthesis level. There is repositioning of your latches to eliminate the hazardous activity, because we have already seen that hazardous activity or the glitching activity. Okay, when it is propagating through several stages. Okay, so at last it will be greater than your logic one also. Okay, so that itself will create a level of output. Okay, so that should be avoided. Okay, so you know that static 0, static 1, dynamic results, etc. Okay, so these hazards to be avoided, so that can be avoided with the help of just appropriately repositioning the latches, appropriately repositioning the latches, so that we can eliminate these hazardous activities. And we can go for pre-computation logic also. So we'll see pre-computation logic in detail while seeing each of the levels of optimization. And the physical design level, okay, at the physical design level, we can try to vary the transistor sizing, okay. So we can increase the width and length of the transistors that will decrease the delay and decrease the voltage, but increases the capacitance and increases power dissipation. Okay, so that means you cannot keep on decreasing or you cannot keep on increasing. An optimal value of W by L values, okay, should be appropriately fixed so that the power can be reduced. Okay, so optimum transistor size is very much required. Okay, and apart from that, again at this stage also, we yes, excuse me. Okay, so then we have adiabatic switching again here also. Okay, so already we have seen that there is unused energy will be recycled back to the supply itself. Okay, so there is the signal energies which are stored in the circuit capacitances may be recycled. Okay, instead of unnecessarily dissipating it. Okay, we can recycle it back, and there is adiabatic switching that can be applied at this physical design level also. And we can go for self-timed circuits with selective adjustment of supply voltages. Okay, so self-timed circuits. There is we can try to adjust the supply voltage with the help of self-timed circuits. Okay, so by adjusting the supply voltage, again we can reduce the power. Okay, so that means redundant transitions. Okay, so repeated transitions will be avoided here. And again, there is at the partitioning level, the floor planning level, placement level, and routing level also, we can try to reduce the power. Okay, so this is how the various techniques are actually applied at each of the level. So we'll see some of the techniques in detail. Okay, so which are used for the power reduction. Next, we have the circuit level. So the circuit level power reduction, we have transistor and gate sizing. Okay, so just now we have seen the physical design level, we can go for the transistor sizing. So the circuit level, transistor and gate sizing can be done. Then we can go for network streaming restructuring, and then we can make use of special latches and flip-flops also. Okay, so transistor sizing for leakage, power reduction, and speed increase. Okay, so here you can see that the first case, the WPL value is 20 by 1, and for the PMOS, and for the NMOS it is 10 by 1, and the rise time and fall time is 1 and 1, and the leakage power is equal to 1. So these are all now readily available results which has been taken from the literature. And for the next case, if we see the WPL values of your NMOS and the PMOS values are not taken, not changed, but the fall time is changed to 2 now, and because of that, the leakage power is now reducing to 0.1. Okay, from 1 to 0.1, we could achieve. And similarly, when we proceed to the next case, where the PMOS WPL ratio is varied, and along with that, we are trying to vary the rise time to 0.5 from 1. And here also, again, if we see the leakage power is equal to 1. So, like that, for varying values of W by L with appropriate rise time and fall time values, we can see different leakage powers in each of the configuration. Okay? So, by appropriately sizing the transistor, sorry, the second case I told we have not changed the W by L value, but the NMOS W by L value is changed to 2. Instead of 10 by 1, it is 10 by 2. So here you can see that there is a reduction in the leakage power. Okay, so for all the cases, the static probability is 0.99, but at the same time, the leakage power is very much reduced in the configuration for the specification which is shown at the center. Yeah. So, likewise, by appropriate transistor sizing, we can reduce the power. We can reduce the power. Okay. Okay, so the transistor sizing for low power. So there is for small WBLs, we will have lower capacitance and higher voltage. And for large WBLs, we will have higher capacitance and lower voltage. Okay, lower voltage. Okay, so large sized devices are used for multiple interconnect dominated designs are used, and minimum sized devices are used only for optimal for low power. Okay, so appropriately we can try to vary every time the W by X, and then appropriately we can fix the W by X for power reduction. Okay. And in network restructuring, again, if you see, there are 4 different circuit implementations for the same function, y is equal to a. Okay, so the 4 different configurations are shown here. But even though though all are implementing the same function, the power consumption for all the 4 structures will not be the same. Okay, it is going to be different. So just by trial and error basis, okay, so we can implement the same function using different structures, and then the structure which is having very low power consumption can be selected. Okay, so in that way also we can reduce the power. And using the special latches and flip-flops, we can go for a dual edge triggered flip-flop so that the frequency will be reduced by half. Okay, so that the power can also be reduced. So in that way, by going for special latches and flip-flops also, we can reduce the power at the circuit level. And next we have the logic level. So in the logic level, we have several techniques. Okay, so the first one is the local restructuring. Restructuring, if you see, we have several rules for restructuring. Okay, so there is decompose and duplicate. There is okay, so decomposing and duplicating. Okay, so here if you see, these rules will help us to separate the critical part from non-critical parts, so that the data can be sized to. Okay, so for that purpose, we are applying the decompose and the duplicate rule. And then we have delete wire. Okay, so that rule actually reduces the circuit size. Okay, delete wire reduces the circuit size. Okay, here you can see A does not have any influence. The second configuration, if you see, the A which is having the input A does not have any influence. So that wire can be deleted. That wire can be deleted. Okay, so by reducing it, okay, we can reduce the circuit size. We can reduce the circuit size. But at the same time, if you see in the next case, add wire, that helps to provide an intermediate circuit that may eventually lead to a better one. So here you can see, we are introducing one more, that is one more input, okay, which goes to the final OR gate from gate. Okay, so that may be different, okay, as far as the power point of view is concerned. Okay, so by applying these local restructuring rules like decompose, duplicate, delete wire, add wire, etc., we can reduce the power. And the next one at the logic level is signal gating. Okay, so signal gating, so if any of the signals, if you want to gate or if you propagate that particular signal, if it creates unnecessary or unwanted switching activity, then we can properly identify the particular signal and then we can stop the propagation of that signal by gating circuits. So what are the gating circuits that can be used? Okay, so we can make use of a simple AND gate because that can act as a controlled switch. By controlling one of the input, we can control the propagation of the other input. Okay, so we can call that AND gate as a controlled switch. So the AND gate itself can be used as a signal gating circuit. Or otherwise, we can go for a tri-state buffer. Okay, by appropriately giving the control signal, we can stop the propagation of the signal. Okay, we can stop the propagation of the signal. So tri-state buffers can also be used. And apart from that, we have latches and transmission gates. Okay, so by appropriately giving the clock signal, or if you avoid the don't give the clock signal, then your input cannot propagate to the output in the latch. And similarly, here also in the transmission gate, the control signal can be appropriately given in order to stop the propagation of the signal. Okay, so the signal gating is mainly to mask the unwanted switching activities from propagation forward, causing unnecessary power dissipation. Okay, so that can be done. And signal gating circuits can be used for clock gating also, because clock signal is one of the signals which consumes more power. So for clock gating also we can make use of these circuits. Okay. But properly we have to identify, so the decimal logic also should be there. So that creates extra area, because the area will be more, but at the same time we can reduce the power. Okay, so there is no one-stop solution for all the problems. Okay, so if we have one solution, that may the objective function will be only to optimize one cost function. Okay, it will be used to optimize only one cost function, and because of which sometimes the other cost functions will be increased. That is, either it will be degraded or it will be improved. Okay, so we do not. So there is no single solution for all the problems. Okay, so this is signal gating, and next we have the logic encoding. Okay, so the logic encoding, already we have seen that switching activity plays a major role, and it is having a major influence in the power consumption. So if you compare the binary and the gray code, okay, you compare the binary and the gray code, okay, so the sequence of the binary code will be in the straight binary sequence. It will be, say for example, for 3-bit pattern, it will be 0, 0, 0, 0, 0, 1, and so on up to 1, 1, 1. Okay. And if you see the number of towers from the last one to the first one, that's all ones to first, all zeros. Okay. There you can see the number of towers is nothing, is 3 actually. Okay. And again from 0, 0, 0 to 0, 0, 1, if you proceed, the number of towers or the number of switching activity will be 1. And again from 1 to 2 will be 2. And for every sequence of consecutive representations, if we proceed, so this will be the number of toggles that is listed in the second column. Okay, this is listed in the second column. So similarly, we proceed to the gray code. Okay, the gray code is the unit distance code that is known to us, and you see the switching activity or the number of toggles there. There you can see the number of toggles is that is 1. Okay, so if you calculate the total switching activity, it will be more in the case of your binary code, be less in the case of the gray code. Okay, so that is for a 3-bit sequence. The number of bits are varied, okay, starting from 1, 2, 3, 5, and 6. Okay, so we can generalize the number of toggles in the binary as well as gray. Okay, so the binary will be 2 into 2 n minus 1. Okay, and for each of the bit, you can calculate what is the number of toggles, and that is listed here. Okay, it is 2, 6, 14, 30, 62, and 126. But in the case of gray code, the number of toggles will be always 2 power n, and there also you can see the number of toggles listed. And if you compare the number of toggles in the binary, okay, the gray code will have less number of, yes, please. So the number of toggles in the gray code will be less. Okay. So for 1, it is uniform. For a single bit, it is uniform. And for 2 bits, if you see, from 6, it is getting reduced to 4. And for 3, it is 14 to 8. Okay. And 30, it is 16. So when the number of bits are getting increased, okay, then slowly almost 50% of the switching activity is getting reduced. Switching activity is reducing by 50%. Okay. So that means if you want to go for any addressing sequence, okay, gray codes are well suited as far as the power consumption reduction is concerned. Okay, so here you can see that there is the ratio of number of toggles with respect to binary and gray is given, and that is getting increased from 1 to 2 almost. Okay, for a number of bits of 6, that is 1.9, okay, it is almost 2. Okay, so that is 50% it is getting reduced. 50% of the switching activity is getting reduced. Okay. So the next technique is the bus invert encoding. So bus invert encoding. So we normally used to transmit a sequence of data, okay, inside a bus, and we all know that bus is nothing but the collection of wires. Okay, and the consecutive sequences, what we are transmitting in the bus may lead to higher switching activity. Okay, say for example, first time I'm sending a 5-bit sequence of 0, 0, 0, 0, 0. Okay, so all 5 bits are zeros. And the next time If I want to transmit all ones, then the total number of switching activity will be 5. Okay? So all the 5 bits are getting or having transition. Okay? All the 5 bits are transition. So the switching activity is higher. So before proceeding to the transmission, if we are able to compare the previous sequence with the present sequence, and then based on that, if we are able to make some decision, like instead of transmitting the true form of the current sequence, we can go for the complementary form of the current sequence. But appropriately, the receiver should be informed that the complementary form is the transmitter. In that case, we can avoid the switching activity. So that is instead of all ones, again we can transmit all zeros, which is the complement of that one. But only thing is we have to send an information to the receiver stating that the complement of the signal is actually arriving or transmitted. So that the decoder which is available at the receiver will properly decode and then it will get the original signal of all ones, all 5 ones. So like that is called bus invert encoding. So for this we have to go for a compromise of decision logic. Okay, we have to go for a compromise of decision logic. And that decision logic will definitely increase the area. Okay, so we have to carefully see that the power consumption of the decision logic should not bother or it should not be greater than the switching activity. It should not be lesser than the switching activity power. That is the power due to the switching activity. Okay, so if we are able to decide that, then we will be able to introduce the decision logic in order to go for your bus invert encoding. Okay, so that way we can reduce the power consumption. Okay, so here just a comparison for your regular bus and the invert bus is given. How much is the reduction in the switching activity? And here also you can see that the switching activity is considerably reduced in the case of your invert bus. Okay, invert bus. So bus invert encoding can also be applied for the power reduction. So next we have the state machine encoding. Okay. So whenever we do the state machine design, okay, so every time we try to have the state assignment. We try to have the state assignment. Okay, so the first case here, 2 state assignments are given. Okay, 2 state assignments are given. Okay, so that is the state you have 0, 0, 0, 1, 1, 1. Okay, so if the assignment is changed, that is instead of 0, 1, if it is 1, 1, and then if it is 1, 1, if it is 0, 1 instead of 1, 1. Okay. So that case, you can see that the expected number of bit transitions in the state register, that is E of n. So that is where for each of the transition. Say for example 0, 0 to 1, 1, we have 0.3, and then for the 1, 1 to 0, 0 transition, it is 0.4. Okay. So the expected number of transitions for the state change. Okay. So that is listed there, 0.3 and 0.4. And then for the same state case of 1, 1, we have 0.1 as the expected number of transitions. Then again from 0, 0 to 0, 1 it is 0.1. And from 0, 1 to 1, 1 it is 0.2. Okay, so just by changing the state assignment, the binary assignment. Okay, so here you can see now 1, 1 is here in this case also the expected number of transitions remains the same. Okay, only the binary assignment is changed now. So now if we calculate the E of m, okay, we calculate the E of m for machine 1, that is your FSM1, and then FSM2. See, so 2 into 0.3 plus 0.4. Okay, for the first case. Okay. Because 2 transition, that's 2 switching activity takes place from 0, 0 to 1, 1. So it is 2 into 0.3 plus 0.4 plus 1 into, okay, so it's 1 into 0.1 plus 0.1, because for the 0.1 if you see, okay, so it is for each of this transition, it is only 1 bit change. Okay, it is only 1 bit change. So it is 1 into 0.1 plus 0.1. So that gives us 1.6 for the first year person. And for the second episode, if you see, E of M2. E of M2. So now, instead of having 1, 1, now we can place we have 0, 1. Okay, so the number of transitions is only 1. Okay, so the number of switching activity is only 1. So 1 into, again, 0.2 plus 0.1, again into 0.1, sorry, plus 0.1. Then again, on the other side, if you see, on the 2 switching, 0, 0 to 1, 1, we have 2 into 0.1, 2 into 0.1, okay? So that gives us 1, okay? So the E of M1, there is expected number of transitions in M1 is 1, for instance, and the expected number of transitions in your second FSM is 1. So the second one can be preferred as far as the power point of view is concerned. Okay, so this is called state machine encoding. So by appropriately having the state machine encoding, we can reduce the power. Okay, we can reduce the power. Okay, so similarly, the output don't care encoding can also be exploited for the power reduction. That is proper assignment of don't care signals. Okay, with the 1 or 0 can also be used for reducing the power, so that we can reduce the expected number of transitions in the output signal also. Okay, so instead of having it don't care, we can fill the don't care with a 1 or 0 as per our requirement, so that appropriately we can reduce the power. So next one is the pre-computation logic. This is also one of the power consumption reduction technique which is applied at the logic level. Okay, so here we are trading the area for power. So what is pre-computation logic? Okay, so from the name itself we can understand something is done a priori, that is before computation, that is before making making your signal to propagate. Okay, we are trying to control here. Say for example, if we want to compare two numbers, okay, so and my numbers are say 1, 1, 1, 0, 1. And the second number is 0, 1, 1, 1, 1. And if I want to compare these two numbers, so for comparison, always we proceed from the MSB. We always proceed from the MSB. So from the MSB, bit itself, we can conclude, that which number is greater and which number is smaller. Okay, so once if we are able to conclude with the MSB bit itself, then what is the need for propagating the remaining bits? What is the need for propagating the remaining bits? Okay, so in that case, what we can do is these MSB bits can be considered as a pre-computed inputs. Okay, these MSB bits are considered as a pre-computed inputs. And if we are able to make the decision based on this pre-computed inputs itself, then the propagation of the other bits can be stopped. Okay, so that it will avoid the unnecessary switching activity inside the circuit. If we are unable to come to the conclusion, then we have to compare all the bits. That is the point. But we are able to make a decision based on the MSB itself, then in that case, propagation of the other bits or the other signals inside the circuit can be stopped. Okay, so that is what given here. You can see that you can now correlate with the comparison of bits with this particular block diagram. So here you can consider that the pre-computed inputs are your MSB bits, okay, and the remaining bits are gated inputs. So we can gate the remaining inputs, okay, by making a decision based on the pre-computed inputs. So if we are able to come to a conclusion that which number is greater than the which number from the pre-computed inputs input itself, then appropriately we can control the propagation of the gated inputs, so that the amount of switching activity can be reduced. Okay, so that is all about the pre-computation logic. Okay, so in pre-computation logic itself, we have several architectures. Okay, so we can choose some of the architectures based on our application. Okay, so and we can minimize the registers also. Okay, we can minimize the registers also. There is the register minimization can be done by lifetime analysis. Okay, so lifetime analysis procedure, and that is a procedure which is used to compute the minimum number of registers required to implement a DSP algorithm in hardware. Okay, so here you can see the specification that is given. So here we have three variables, that is A, B, C, which are involved in a particular computation. Okay, so that A lives for 3 time units or 4 time units, that is 1, 2, 3, 4. And the variable B lives during the time units 2, 3, 4, 5, 6, 7. And let the C live during the time units 5, 6, 7. Okay, so for which we can draw the lifetime chart. Okay, so with the representation of your units, time units starting from 0, 1, 2, 3, 4, 5, 6, 7. And for each of the time unit, what is happening? So during 0 cycle, none of the variables lie, so that is 0. And for time unit 1, we see for the time unit 1, only your A is alive. Okay, so A is also only one variable. And for the time unit 2, if we see the variable A and B are alive, so 2 variables are alive for the time unit 2. And for time unit 3, it is again 2. Okay, for the time unit 3, again it is 2, that is variable A and B. Okay, so like this, we can list the number of variables which are alive, okay, for each of the time units. So based on this, we can decide on, okay, so even though 3 variables are there, we don't require 3 registers here, okay. So at the maximum, what we require is only 2 registers. So using this lifetime chart, okay, linear lifetime chart, we can decide on the number of registers required. Okay, so if we proceed directly, okay, without this analysis, the number of registers, the usage will be maximum. Okay, and that can be minimized. So by register minimization also, we can reduce the power. Okay, we can reduce the power. Okay. So next we have the architecture and system level of power reduction. So that is which we have operation reduction. Okay, operation reduction. So operation reduction is reducing the operations and maintaining the throughput. Okay, maintaining the throughput. So in the first case, if we see the function which is getting implemented is x square plus x8 plus b. Okay, so first we are evaluating x square with the one multiplier and the x8 with another multiplier. And these two are summed up in order to get x square plus xa. And then finally, your b is added. So for the implementation of this one, we can see that 2 multipliers and 2 adders are required. 2 multipliers and then 2 adders are required. Okay, it's the same thing. Okay, so we know that instead of having x square plus xa plus b, we can also implement that in this form. That is xa. Okay, x and a are added up first. Okay, so we get x plus a. Okay, so there is the first 2 terms we are trying to take x common. Okay, that is normally we used to call it as sub expression elimination or sub expression sharing. Okay, so those concepts which are used for numerical strength reduction can be applied here also. So here the expression x square plus xa plus b, we are trying to take x common outside. Okay, so that we get x plus xa, sorry, x plus a. Okay, so instead of going for x square generation and then xa generation and then proceeding for x square plus xa, so here you can see x plus a is generated first and then that is multiplied with x and then finally a b is added so that one multiplier will be reduced. Okay, so the same function is implemented and the throughput is also same because if you see the critical path, okay, so the logic depth is also same, the critical path is also same. Okay, but we are able to reduce one multiplier. We are able to reduce one multiplier. So instead of approaching the implementation directly, we can explore the avenues. Okay, whether the operations can be reduced or not. So that will definitely lead to reduction in the power. Reduction in the power. So this is one simple case where we can able to see or we can able to reduce one multiplier for the same function. Okay, for the same function, the same throughput. And we can, that is reducing operations. And here also, we can reduce the operations with less throughput. We can reduce the operations with less throughput. Okay, so here, this is an example where we can reduce the number of operations. Again, the throughput is also reduced. Okay, the throughput is also reduced. So in that way also we can do it. Okay. Okay, so at the architectural level, we can employ parallelism. Okay, so parallelism is used to reduce power dissipation at the expense of area while maintaining the same throughput. Also, multiple outputs can be obtained in parallel in a clock period. Okay, so the effective sampling speed is increased by the level of parallelism. So there is a concept between the parallelism that is known to us, and the register. Consider that your register is supplying 16-bit operands. Okay, it is supplying 16-bit operands, and the register is clocked at a maximum frequency of 50 megahertz. Okay, the register is clocked at a maximum frequency of 50 megahertz, and the worst case delay of the multiplication is 20 nanoseconds at a V reference of 3.3 volts. Okay, at a voltage reference voltage of 3.3 volts. Then what will be the estimated power dissipation? So for which you can calculate this particular system, we can take it as a reference. And then we'll proceed to the parallelized architecture and the pipelined architecture. In those cases, how the power is getting reduced when compared to this reference architecture. That we will try to analyze. So the estimated power dissipation is P reference is equal to C reference into V reference square into F reference. So that is the same expression what we have derived for the dynamic power in the earlier slides is listed here again. So that is P is equal to CB square F. And C reference is nothing but the summation of all the node capacitances, okay, along with the switching activity pattern. That is sigma Ca alpha. Okay, so that is the C reference. So that is the uniprocessor. Okay, so what we have seen, the power expression is for the uniprocessor. So here is the 16-bit operands are supplied by two registers. Okay, there is two registers are there. Both the registers will be supplying the 16-bit operands to the 16 cross 16 multiplier. So there you can see it is a uniprocessor. Okay, so we are not gone for any parallelism or pipeline. The next stage or the next diagram we see where the same architecture is getting replicated. Okay, so it is exactly doubled. Okay, and then finally the output is selected through a multiplexer. The output is selected through a multiplexer. Okay, and here we'll see what is happening. So because of this parallel processing, okay, that is we have even though the area is increased, the power will reduce. Let's see how it is getting reduced. So the computation of the multiplier is parallelized by duplicating the multiplier 2 times. So it maintains the same throughput as in the case of the reference architecture. So the throughput is going to be the same. So the input registers are clocked at F reference by 2. That is 25 megahertz because the registers are clocked at a maximum frequency of 50 megahertz. And that is now getting reduced to half. So 25 megahertz. 25 megahertz. So the power supply can be reduced to achieve a worst case delay of 40 nanoseconds. Okay, so we are trying to reduce the power supply to achieve a worst case delay of 40 nanoseconds. So in this case, the power supply can be reduced from 3.3 volts to 1.8 volts. That is, by reducing so, we are trying to maintain the worst case delay of 40 nanoseconds. So in that case, we can divide the reference by 1.83. So the effective capacitance has increased by a factor of 2 due to the duplication of the circuit because the multiplier architecture is doubled, and because of that, the capacitance will also be doubled. So that is, with reference to the uniprocessor architecture, okay, it will have 2 times of its capacitance. So however, due to the extra routing, this effective capacitance is around 2.2 C reference. Okay? So even though the capacitance is doubled by an amount that is doubled because of the routing, extra routing, again we are adding 0.2 times of your C reference as a routing capacitance. So if we substitute all these cases, in the case of your power consumption of the parallel architecture, then the C reference will be now 2.2 times of C reference, and V reference is that will be divided by 1.83. So VDD square, so it is squared, and then instead of F, now F reference will be divided by 2. Okay, F reference will be divided by 2, and then if we calculate all the numerical values, then the expression for your parallel architecture will be T parallel is equal to 0.33 times of V reference. Okay, so now you can see that this is just not an exact result. Okay, it is not an exact result, but the trend of the results will be the same. Okay, so there is, you can see that it is only the power is only 0.33 times of your reference architecture, that is uniprocessor architecture. So that is actually what this expression concludes. Okay, so the power will be reduced when compared to the reference architecture, and the same uniprocessor architecture can be pipelined now. Okay, so the architecture can reduce the power dissipation. Okay, so it leads to a reduction in the critical path. Okay, when we pipeline the architecture, it will lead to a reduction in the critical path. So either increases the clock speed or reduces the power consumption at the same speed in a DSP system. So again, we are considering the same uniprocessor architecture. There is 16 multiplier with 15 megahertz multiplier is broken into two equal parts. So a set of pipeline registers is inserted, resulting in this two-stage pipeline version of multiplier. So here you can see the same multiplier is broken into half. So we have two half multipliers, and in between we are having the registers. In between we are having the registers. So at the input stage we have a register, and the intermediate stage between here half multipliers. Okay, we also we have a register. Okay, and here you can see we have performed the pipelining, and because of that, what is happening to the capacitor voltage? Okay, and the frequency that we will see now. So since the hardware between the pipeline stages is reduced, then the reference voltage V reference is equal to 3.3 volts. Can be reduced to 1.8 volts again. So again, your V reference will be divided by 1.83 to maintain the worst case delay of 20 nanoseconds. Okay? So that is 50 megahertz. So the estimated power dissipation for this case will be, we have not gone for the duplication of the architecture, only the extra registers we had. For that, we have considered 0.2 times of C reference. So totally it comes to 1.2 times of the C reference. And the voltage, as far as the pipeline architecture is concerned, it remains the same, that is V reference by 1.83 the whole square. And that into the frequency is not reduced by half here, so it is F reference 12. Okay, again, if you we calculate the numerical values, it comes to 0.36 of the reference architecture. Okay, so the power consumption of the pipeline architecture will be only 0.36 times of the reference architecture. Okay, so by employing parallelism, parallelism and pipelining concepts, okay, we can reduce the power. Okay, so again, we can go for distributed processing also. By distributed processing, okay, so even though the area is getting increased, okay, the power will be reduced. We told we can go for retiming. So by retiming, for a non-retimed circuit and the retimed circuit, we can see. Okay, so the speed will be increased. Okay, so again the power consumption will be reduced, and also for holding architecture also, by going for holding architecture, then we can reduce the power. Okay, so up to this we have seen the various techniques which can be applied for the power reduction at the various levels of design abstraction in VLSI design. Okay, so now we'll see one or two case studies. Okay, so there is test power minimization in VLSI circuits with the reordering technique. So the basis for this particular work is the switching activity reduction. Okay, so from the discussion, we understood that by reducing the switching activity of the circuit, we can reduce the power. Say, what is this test power minimization? Say, for example, if I want to, I'm designing a full ladder. Okay, I'm designing a full ladder, and if I'm applying the inputs, there is input stimulus for it, and then if I analyze the response, then I can analyze the correctness of its functionality. So, but in what order we are going to apply the input? Okay, if I apply it in the straight binary order, okay, then it consumes more power. At the same time, if I try to reorder the input vectors so that the minimum switching activity can be obtained, so in that case, definitely the power consumption can be reduced. So that is what we have tried to investigate in this particular work. I'll just move very fast. Okay, so in the test generation technique, we have several techniques like path sensitization, Boolean difference method, okay, D algorithm, codem algorithm. So like that, we have n number of algorithms for the test generation for any logic circuit. So here we have used the path sensitization method in order to generate the test vectors, So after the test generation, we actually wanted to minimize the switching activity, for which we have applied three of the distance measures, that is having distance, verse key index, and then unit distance code, etc. Okay, so as far as the distance measures are concerned, we have several distance measures like Mahalanobis, and we have Euclidean distance measure, Euclidean distance measure, like that. We have n number of distance measures also, and each one has its own properties and features. And here, what we have selected is having distance, verse key index, and then unit distance code. So using these three distance methods, okay, distance measures, we try to reorder the test vectors what we have generated. Okay, so after reordering the inputs, then we applied for the circuit for the testing, and for which we have considered some of the benchmark circuits, simple benchmark circuits like which are available in ISCAS benchmark circuits. Okay, so we have taken simple circuits like C17, etc., and then we have tried to evaluate the power. Okay, so after evaluating the power, we could able to find that the binary Mirsky based reordering technique reduces the switching activity considerably, and the power consumption also reduces, when compared to the other distance measures. Okay, so like that, we can. This is not only for the test power minimization. For any addressing scheme also, we can try to reduce the switching activity by going for such kind of reordering of the inputs. So reordering of inputs, okay, with an objective that to reduce the switching activity, it will definitely reduce the power consumption. So this we have tried, and probably the time is up, so I'll try to skip the power estimation part, that is power analysis part, because most of the time we try to rely on the tools for the power estimation or the power analysis. Okay, whether it is a circuit simulator or it can be an high-level simulator like there is a circuit simulator like SPICE, P-SPICE, H-SPICE, or whatever it may be, or sometimes we may go for higher level simulators like there is Verilog, VHDL, there is Xilinx based tools. Okay, so most of the time, since we depend on the tools for the power analysis, okay, so what are the types of power analysis available? So that probably I'll try to keep the presentation, okay, so that you can go through that later. Okay, so directly move on to the other two power estimation case studies which we have done. Okay, so it was given the how to estimate the power using Xilinx tool, that is with the help of X power analysis. It's more for most of you it may be known. Okay, so just for the estimation purpose, I've given that, and also in the cadence also how to estimate the power. Okay, so that flow also I have given here. Probably you can go through later. Multiple simulation is also very much required, because whenever we wanted to vary the process parameters, then we can sweep those process parameters with the help of Monte Carlo simulation, so that we can prove that our design is robust even for variation in temperature, even for variation in on-site thickness, even for variation in the threshold voltages. Okay. So that can also be proven. Okay. So in this work, what we have done is we have gone for a power estimation using neural networks. Okay. So neural networks is the different concept. We all know that most of the time neural networks is used for classification purpose. But in this work, we try to use the neural networks, that is a back propagation neural network and the radial basis function neural network for power estimation. That is, in order to predict the power, okay, in order to predict power, we have made use of the neural networks. Okay, so we have configured, that is, we have taken two neural networks. One is the back propagation neural network, another one is the radial basis function neural network, and we have taken the benchmark circuit details. Okay, discuss benchmark circuit details, with that is, we have taken the attributes such as the number of inputs, number of outputs, number of feedback blocks, number of inverters, number of gate count, that is the gate count, then number of AND gates, OR gates, and the NOR gates. And by using these attributes, we have tried to train the neural networks, and then we have tried to test the neural network also. So after testing the neural network, we have done the regression analysis also. Okay, so using the regression analysis process, we try to establish the relation between a dependent variable and one or more independent variable. Okay, so after testing, we were able to get, okay, so after the regression analysis, if the regression value is closer to 1, that means the prediction or the estimation is very accurate. Okay, it's accurate. So by varying the configuration, you know that in neural networks you will have the input layer, then hidden layers and the output layers, and in each of the cases the number of neurons, everything can be varied. Okay, so we have tried to vary the number of inputs. Okay, the layer size also we have configured in different cases, and also we have tried to vary the learning rate. Okay, so the learning rate and the number of inputs, that is training, and we have tried to analyze the slope and the y-intercept and the regression. And based on the regression value, we could able to find out that the regression value is very closer for some of the cases. That is, the neural network was able to estimate the power, okay, for the circuits. And these are all some of the results that we come to be interested. And we have tried to vary the activation factors also, there is activation functions also. And we have used different training algorithms also for the back propagation neural network. And for each of the case we have analyzed, and for we were able to find out that train SCG, that is train SCG stands for scaled conjugate gradient algorithm. So that algorithm, all are inbuilt in MATLAB, and all these algorithms are inbuilt in MATLAB. So as far as the implementation is concerned, we have not gone for any modification, but we just wanted to know how far this is effective in estimating the power, okay, for VLSI circuits. So as an attempt, we have tried this, and we were able to get a maximum value of the regression in both cases, that is the back propagation, radial basis function, neural network. In both cases, we were able to get an accurate power estimation results. So that is what is projected or highlighted here. Okay, so, and this is the, to summarize that for training function with variable learning rate, train RP was better, and quasi-Newton training function category, train basis mode, that training algorithm was better. And for conjugate gradient category, your train SCG was better. And for which layer it was better, that is also given the layer size, that is 8:15:16:1, with inputs distributed for power estimation. So there may be a question that when there are power estimation tools, what is the need for neural networks? Okay, so there every time that you have to develop your circuit, you have to implement your circuit, and then only you have to study the power. That is, you have to evaluate the power. So here, with the details of how many number of inputs, how many number of outputs, what are the types of gates present, okay, how many flip-flops are there, with those details, with a quick, in a quick way, we can find out what is the power. Okay, what is the power? So this is just an estimate. Okay, so the actual scenario we have to go for, if you want to calculate the power in accuracy, then we have to go for the circuit level simulators only. So using that, we can find out the accurate power. But before proceeding itself, in order to have an idea of how much power the design can consume. So that can be applied using such type of statistical analysis methods. Okay, so that is the point because of which we tried this work. And similarly, after that, after creating that, again that neural network model was incorporated with fuzzy. Okay, and then again we have again made it adaptive also. Okay, so based on that, we have brought for publication also in the International Journal of Electronics. Okay, so that is Taylor and Transistor. Okay, so that is adaptive democracy inference-based system-based power estimation method for CMOS VLSI circuits. And we have done the analysis, and we have made the answer system, okay, and then we have used the same training algorithms. And again, we have calculated the regression analysis also, and then we have calculated the root mean square value. And we were able to, when compared to the BPNN itself, we were able to get good results with the answers. Okay, so that also we have obtained. And the power estimation using neural network, one more work. Okay, so that was also published in one of the Springer journal, that is design automation for embedded systems. Okay, so there are a lot of avenues as far as your low power design is concerned, and most of the concepts are all well known to us. All the concepts are well known to us. The only thing is that while doing a design, we have to create the design as a power aware design, and also not only power aware design, it should be, we should be able to bring out testable designs also. Okay, our design should be I think we should be able to test our design also. Okay, so for testability also we can incorporate DFT measures like controllability, observability. Okay, so those concepts can be incorporated inside the design, and then we can make our designs as power-aware designs. Okay, so that we cannot address all the power issues, at least to the maximum, whatever is possible. That we try to reduce, so that okay, so the design can be an energy efficient or power efficient design. So whenever we do the design, we have to always concentrate on these things. That is request. Okay, so with this, I conclude my session. That's all from my end, and I'm extremely sorry for skipping most of the slides because I prepared it very heavily, so that I was in a position, because of the shortage of time, I was in a position to skip those slides, but I'll try to leave it in the material. You can go through data, but all the concepts are unknown to you. Nothing is new. Okay, so only thing is while doing it, we have to recall those things, and then we have to incorporate that. That's all for my very soon. We'll discuss.
Hello.
Yeah, please.
Audience, do you have any queries or questions? You can.
Yeah, I have a query. Am I audible? Yes, I have
Yes,
a
ma'am,
query.
you're audible.
Am I audible? Yes. And the last point that in this slide is mentioned that the aggressive reduction of the supply voltage is the most effective technique. Probably you mentioned earlier. I may skip those. I cannot concentrate there. But can I please elaborate that how much we can reduce? That what is the limit that up to which I can reduce the supply voltage? We cannot go beyond that.
Yes, madam. Actually, now nowadays we are concentrating on 5 nanometers, 7 nanometers, etc. So for those designs, we are going up to 0.6 voltage. 0.6 voltage. But we cannot keep on reducing it, because every time when we try to reduce the power or energy, we have to parallelly look after the delay also. So we have to calculate what is the power delay product and then what is the energy delay product. And we have to fix an optimum value, because we keep on reducing the power or the energy, that will definitely reduce the speed. Okay, so we have to
Okay, it is related with the delay parameter. So the delay will increase if I reduce that.
Yes, madam. Yes, madam. So
Okay,
because of
so
that,
we have to keep a balance.
yeah, we have to keep a balance. So up to now, for point, sorry, 5 nanometers and 7 nanometers for those designs. I think they have used 0.6 volt sometimes. So, but that cannot be reduced fully, but always we have to take an optimal value of the supply. But whatever, say for example, if I'm using a 1.25 micron technology, in the technology I should not work with 3.3 volts or 5 volts. The technology is meant for 1.2 volts or 2.5 volts. Okay, so like that we have to reduce. With the available technology features, we have to reduce the supply voltage. But at the same time, we have to look after that the delay is not becoming worse.
Okay, sir. Thank you very much, sir.
Thank you, madam. Thank you. Thank you for your understanding.
Audience, you have any more query, question, or any discussion you need?
There is chat box also you please look after. I am unable to see that clearly.
Good afternoon, sir.
Good afternoon, sir. Please tell.
Sir, suppose I want to design some LNA or some mixture, and in that case, if I'm using a CMOS, like suppose 90 nm or suppose 65 nm, and in that case, because we are having two topologies which are fixed, like common gate and common source, so in that case, how we can reduce the power? Because we are talking of voltage, then it is fixed, like 0.7 volt or 1 volt or 1.2 volt. Then
Yeah. Well said, sir. Well said. Actually,
that
as
is
you
my
said,
question.
yeah, for digital circuits, the supply voltage is reduced considerably. But that is not so in the case of your analog circuits. For analog circuits, the power reduction is, the supply reduction is not that much equivalent to the digital circuit. So while going for analog circuit design, say for example, I'll just tell you one work what we have done. Actually, we wanted to test A to D converter, analog to digital converter, and we all know that a RAM signal is very much required for testing the analog to digital converter. And what we have done is we wanted to develop a built-in self-test architecture for that A to D converter. So we thought, okay, how effectively we can design a RAM generator circuit that can be brought into the chip along with the A to D itself. Okay, so there are several techniques, but we wanted to go for a single technique. And in one literature, we were able to find out that using a voltage controlled current source, voltage controlled current source, which can be used to charge the capacitance, the charging region of the capacitance can be made linear, so that linearity can be applied for the testing of the A to D converter. So what we have decided is we have taken all the current mirrors, that is all the current sources, like starting from simple current source to Bridger current source, Wilson current source. So like that, all the current sources we have taken, and then we have made an analysis which current source is actually consuming less power and which is giving higher linearity also as far as the charging of the capacitance is concerned. That current source we have selected, and then we have made use of for our RAM generator circuit, and then that RAM generator was along with the A to D, it was incorporated in the design. So like that only the analog VLSI. So far techniques, whatever we have seen, it is mainly for digital design. So if you want to go for analog design power reduction, then we have to explore by using trial and error methods, and then we have to go for the power reduction technique. That is the only possibility. And as you said, the supply voltage reduction cannot keep on going as like the case of your digital circuits, because here that is not that much improved as far as your analog circuit is concerned when compared to the digital circuits. So we have to do the trial and error basis with the help of a transistor sizing. Sometimes it may help there in the design.
Okay.
Is that convincing, sir?
Yeah, sir. Okay, sir. Thank you.
Thank you, sir. Thank you. Thank you so much. So if any more queries, then try to give convincing answers. So if you have any queries, please come out with the queries.
Audience, participants, you can ask your research-related queries also. Currently, if you are facing any problems, I will be definitely answer. Yeah, there is no more queries. Let me conclude the session. Sir, thank you so much for your valuable presentation, sir. And also thanks for your all support from the beginning of this FDP, which I have organized. Thank you so much, sir.
Thank you, Dr. Ilangovan, for giving me this opportunity. So at this junction, I would like to thank the organizers of this FDP, the Untitled FDP, and GC's Biranga for giving me this opportunity to share some of my experience with the participants. And also, I thank all the participants for your patience. Thank you all. Thank you.
Thank you, sir.
Thank you. Can I leave?
Sir, yes, sir.
Thank
Yes,
you.
sir.
Thank you.
Yes, thank you, sir.
Thank you.
Participants, please make your attendance. I can find some empty columns in the attendance. Please confirm your attendance. If you are finding any difficulties, please put message. And one more thing, the recorded section of this and how much possible, suppose if the resource person, they are ready to share their slides, those things also will be shared with you. Okay, definitely you will get as much as possible materials. Okay, but it will take some time because right now I am concentrating on inviting the resource person and making care of this networks, all the things. So right now I couldn't do. Definitely you will get all the things. Okay, so after Friday, after completing all our sessions, I'll give all materials and all the things which are possible. Fine?
Thank you,
Yeah,
sir.
thank you. Yeah, thank you so much.
Sir, we are not getting attendance link.
Sir,
Attendance link is not there.
the same link, sir, which I shared, the same link you can use.
It is shared on where?
Shared on where? In our WhatsApp group and also in our mail. Have you made any attendance, sir? Never. Is it first time you are going to put your attendance? Have you made your yesterday attendance?
Yes, sir, yes, sir, I have made.
The same link you can open and put your today attendance.
Okay, thank you, sir.
Yeah, thank you. Any more queries or we can leave? Yeah, thank you. We'll meet by the time of our hands-on session. Thank you.